Okay. Huh? Who's David Grotner?
It's first year graduate.
Oh, is he the guy that occasionally shows up to the labs?
He is in rotation program, and if he wants a good grade, he may decide to do the project as well. If he doesn't care, I don't know.
Are we only supposed to sign up for one?
Oh, you can sign up for more, and if you're not sure, I will help you to make final choice.
And only the ones that say help. Huh? Only the ones that say help on the side have helpers available.
No.
All of them have helpers.
Those were indicate helpers. It means that there are either graduate students or postdocs who are really working on this project, and they will help immediately. But for others, is it possible to project?
Oracle on GD1 G1 or D21.
So the main thing is to select projects, right? Anyone missed last? Okay, who was missing? You were not here, but did you watch the recordings?
No, I haven't got a chance.
Okay, well, you can make your first spontaneous choice, and you may decide, because we will start actual work on Wednesday. But I just want to make up some plans and prepare and get ready to help in a specific way to
Pick more than one?
If you pick more than one, it means that you are inviting me to help you to select which one is more promising. So, anyone is interested to submit something? Okay. I like that idea of extra credit. Has some resonance with your credits.
Still full.
And you, you bring everything on Wednesday. This part as well. So there will be some important, relatively important class material, but this chart that you are filling is most important for the remaining part time in the class. So I'm not yet ready this minute, but one day I will come and ask you to raise hands for standard exam or the presentations, and I have an idea how majority will work. So there are about 6 parts of 6 types of projects. The last one is so challenging and novel that there are not much instructions, but there will be if someone is so brave to mention it. And the second last, it relates to material that we didn't cover in class or partially covered, but you have seen this rotating orbitals with music, so it's similar to this. So it's like pedagogical, and there will be another thing that rotates related to angular momentum and speed. The rest, for each section, have two subsections: model and ab initio. So model means that, well, we all are running with packet code in one dimension. And the difference is mostly by choosing the potential. Model, which means that you just creatively, with or without helper, design function for a potential based on your scientific intuition or data from literature. Ab initio means that there will be helpers who will provide computed from reliable programs from detailed atomistic coordinates and exact chemical models, will compute the potentials and will forward them to you. So it will be a little more reliable. I cannot say will it be easier or quicker, it's just a little different look on a problem. So if you open model, it's only you and computer. If there is ab initio, it will be someone helper. And I am using any opportunity to advertise the course that will be offered in spring. The ab initio parts and potentials that I used in this PChem are done by those students who took computational chemistry in the past. So for more exact potentials. So what are the sections? The
Oh, I'm sorry. I didn't notice that.
So the first section is when our coordinate will be coordinate of electron and mass will be mass of electron. There are several opportunities to look how electron moves in one dimension, and the electrochemistry, the semiconductor or interface of semiconductors. There is a thing that was not last year, momentum dispersion. I didn't put helper, but whoever chooses this, I will put helper. And this works really well for interface of donor and acceptor. For the ab initio based, it will be some models that current postdocs and students are processing, like diacetyl solar cells and no fancy perovskite semiconductor for solar cell and light emitting. The section B, so basically A and B are major sections, the rest are its own. Is when coordinate will be not a coordinate of electron, but a coordinate of interatomic distance, or more complicated concept of reaction coordinate when several atoms are moving and experience reaction. The code will work for this chemical aspect as well, but the mass should be pushed like several thousand times bigger to accommodate for nuclear mass. And there one can select combustion or catalysis and select from literature or from your intuitive understanding just height of and width of a barrier, while for ab initio, I didn't put that help is available, but it is very available. So one can choose the actual catalytic reactions when groups radicals come, associate, and then depart from catalytic surface or the combustion. And the section C is cream of the cream, in some sense. So number 1 and number 2, we kind of covered in the labs and in class. The section C was never covered yet, and as Bruce mentioned it last time, it is when electronic degrees of freedom and neutral degrees of freedom change simultaneously. When there is like ground and excited state, and in each of them, the interatomic forces are different. There are different potentials. So there will be crossing potentials. And this is maybe the most innovative part if someone is looking for it. I will leave it here if someone really decides and wants to change their mind until the end of the course, it's fine. So the problem of choice that I would do would be this one. So it is when quantum dot is excited, it changes interatomic forces, and there are transitions between ground and excited with emission phi. This one. Oh, okay. So the advertisement that something is easy and fun was attractive for some people.
Yeah. Something like that.
Okay. Good. Yeah, and we do have 2 people missing, right?
Is that Isaiah and Joey? Yeah.
Yep. So, what are we doing regarding the class material, and what are our goals? They, in some sense, they're not super ambitious after you are becoming experts in this method of wave packet propagation. We, in the next several meetings, we are not going to get more than oscillating wave packet non-equilibrium state harmonic oscillator that changes central position and changes the shape of distribution related to the MATLAB-based homework that you're going to bring hopefully on one day. The technical tool that is auxiliary in getting it is so-called coherent state. And we decided to make a mathematical experiment. What will be the eigenstate of annihilation operator? So most traditional problem is to find eigenstates of Hamiltonian. But sometimes we do crazy things and find eigenstates of something else. So we put operator here, eigenvalue which we temporarily assume known there, and here, what is it?
Wave function.
Unknown eigenfunction, right? It is unknown, but we already add some specifics. So it is a superposition of eigenstates of harmonic oscillator, which are favorite subject for presentation by Michael. Right? And the coefficients are unknown. So in some sense, this is an equation to find the C sub n coefficients. Will it be all zeros except 1, or there will be certain proportions between different coefficients? So we plug in the annihilation operator. We practice zoo of Python and Rabbit, right? to practice this chronicle delta transformation. And on the left part, we rename the indices just for our company. And then we came to the expression where on the left and right sides, we do have a series, an infinite number of favorite states of mind, eigenstates of harmonic oscillators. But coefficients on the left and right side are different in front of given index. And it looks that they are in some relation between each other. So the coefficient in the next number depends on the coefficient from previous number, which was it Ben? Okay, who suggested me the right word? Ben claims. Can you, anyone except Ben can recall the right word? When we do have a progression of numbers or functions, and they are not independent, so they are
recursive.
Yes, recursive. So if we just parse out of this, so this equation means, in fact, set of equations. It means the recursion, this set of equalities for each number n. Okay, cool. Next slide, that's true, yes. So coefficient number n and coefficient number n plus 1 relate to each other in this way. So what is the strategic plan? Again, by now coefficients are unknown. We only know how they relate to each other, but we do want to find all of them. There is nothing lower than beta in sense of letter. So there is the lowest coefficient will be C sub 0. So we can hypothetically assume for 20 minutes, not forever, that we know the value, the eigenvalue, which we call this letter U here, and let's assume that we know C naught. Would it be sufficient to find all other coefficients?
No.
Yeah. We just put 0 here, then it will be 1 here, and we immediately find C1, and then keep the recursive progression. Okay, it was a review, what we did before. And before we keep going further, I'm refining this ugly table from year to year, but I'm not yet at perfection. So please excuse the bad calligraphy and mess. But there is an idea of what we are going to do after our toolbox will be complete. So again, I don't know, maybe your minds are very clear and you have your goals in front of you on your thoughtful site on like your dashboard, but I need to ask myself what I'm doing. So the goal is to predict future of harmonic oscillator in the non-equilibrium state. And we do have from the very beginning of the course, there was a third way to predict future. When we take eigenstates, take expansion coefficients, and take phase accumulation. Does it click something? Remember? We were doing quick quiz, and majority were successful in finishing. So it is here. So eigenstates, expansion coefficients, which depend on the initial condition, and accumulation of phase, which occurs for each eigenstate according to the energy eigenvalue, right? So no one proved us that this is wrong. Therefore, we keep believing it, that this is a right way to predict future. For harmonic oscillator, we know eigenstates, we know eigenenergies, which will be h bar omega times 1/2 plus number of states. And we will select coefficients. As an approximation, as a guess, later on, I will try to establish a connection between this eigenstate of annihilation operator and coefficient that we will choose for predicting future. But we are going to practice this thing, time-dependent Schrödinger equation solution. And it is kind of a chart how we go to observables, which are the goal for any quantum problem, predicting outcome of a measurement. So one starts from time-independent Schrödinger equation, getting eigenstates and eigenenergies, right? Which I used here. One needs to select initial conditions and find expansion coefficients of initial condition over basis, and then there should one more arrow here. And then there is an input of eigenstate, eigenenergies, and this C naught expansion coefficients that enter into this prescription. And then we can go to observables on this practice. Okay. So, where are we going to sit? Where are we going to stop by the end of today's meeting? If it will go successfully and it will be sufficient time. We are going to predict future that we always wanted for harmonic oscillator in specific case of specific initial condition. If our initial condition, if our initial expansion coefficients will be the same as eigenstates of annihilation operator, and right now I'm just offering it as a piece of information, but I will provide logic later. So if eigenstate of annihilation operator is chosen as initial state, then we will get predicted future for how the state evolves in time. So right now, this neither one of these equations is clear. They all are ugly. But the only thing we can recognize the summation and eigenstates, or better here, summation, eigenstates, and here there is a accumulation of phase and some coefficients. But right now it looks ugly. But through several steps of derivations, we are going to prove it, and we are going to love it. It's one of the few problems in quantum theory that can be solved exactly by pen and paper. The amount of solvable problems is very small. It's another reason why quantum theory as part of physical chemistry is hard and counterintuitive, because it's not easy to design sufficient amount of practice problems, because most of true problems are not solvable. Okay. So C n plus 1 square root n plus 1 C n u. Oops, right? Please feel free to catch me lying if I do. So suppose that we know C naught, then C1 will be u divided by square root of 1. U C naught. Then C2, you're probably tired, exhausted, and looking forward for the Memorial Day weekend. Otherwise, it will be really good practice to pull everyone one by one because it is something easy. I do easy something myself. Or maybe offered next year. So C2 will be u will be C1 u square root of 1 plus 1, which will be u divided by square root of 2, and we can plug in the value of C1, right? Which will be u C u square root of 2 times 1 times C2. C3 u divided by square root will be equal C2 u divided by square root of 2 plus 1 because we have here 10 plus 1. U divided by square root of 3. What would be reasonable to plug in? The value for C2 can be plugged in here. U squared square root of 2 C. So u to the power 3 divided by square root of 2, 3 times 2 times 1 C. How do you call multiplication of 1 times 2 times 3?
Factorial.
Super. It's pleasant to be in the surrounding of dedicated people. Do you see the trend? Like this little number 3 and this little number 3 coincide, right? And this number 3. Right. So what will be the general equation for C sub n?
U to n
Yeah. Okay.
over square root of n factorial times C.
Excellent. I have forgotten to look through the list of Nobel Prize holders. I don't remember if Roy Glauber got his prize, but this is a discovery definitely worth of Nobel Prize several years ago. So we do need we were very quick. So C sub n is u to the power n square root of n factorial C naught. Are we happy? Well, to the extent as a human can be happy for equations. Or something is missing. Did we fulfill our original goals? Well, we have so many ambitions and so many goals, but at least the local one. To find eigenstates of annihilation operator? Did we found it? What do you think?
The expansion coefficient, but
We right now we can call it mu eigenstate of annihilation operator is summation over n eigenstate n, and here we can put mu to the power n times c naught divided by square root of n of mu, right? So it will be eigenstate of the annihilation operator with eigenvalue mu. But we do not know mu, which, okay, we can permit ourselves, indulge ourselves for not knowing one constant. But we also do not know C naught. So we have plenty of ignorance about the state. We have general functional form, but we do not know coefficients. And it is a little problem that we can quickly fix. So do you have an idea how to find C naught to be more specific? So some of the problems or choices of the methods can be done without switching on brains. Just it's not a bad word, but it's by combinatorial search. So we have very listed number of methods and tools, and we can just think like, can I solve Schrödinger equation once again? Probably not. So can I try density matrix? Probably no. Do I need density of states? No. Can I practice orthogonality? So can I check if the state is normalized?
probably,
How do you know?
because you're asking in a different
Yes,
way.
I'm just scrolling through available methods in the toolbox and pretending that I'm thinking it really in front of you and I'm getting an inspiration. Oh yeah, normalization, how can I forget about it? So all quantum states must be normalized to 1 if we work with one particle. Before we were working with one electron, now we're working with what is our particle?
A bond.
A bond, okay. It's a tricky question. It's not easy to answer because like it could be a normal mode when several bonds oscillate simultaneously.
Harmonic oscillator.
Oscillator, yes, but physically, chemically, it's oscillating bond. What is one particle that you're going to normalize to? We understand that it's only one particle, but what it is? I don't know the answer. I don't know how to tell it by strict word. Maybe if it will be physics audience, one could say it is one photon.
On what?
No, you know the word photon. When particles of light are
Photon.
photons,
Sorry.
and there are particles of sound, phonons. Or amount of nuclear oscillation energy also is quantized, and one quantum is phonon. But no matter how we call it semantically, all quantum states that we are dealing with in this course are normalized to 1. There will be no exception. Although in the spring course in computational chemistry, there will be exceptions. There will be many molecules. So, what does it mean to normalize? How do we normalize wave functions that are expressed not as continuous distribution in space, but as set of discrete coefficients? So if we have wave function, we need to, I've forgotten how to do stars. It should be 1, right? What if our wave function is represented as a set of coefficients C1, C2, C3, and then C sub n? How to convert equation number 1 in terms of definition number 2?
You make one a identity matrix.
To make or replace, no, normalization should be a constant. It will be not a vector. Let's, I know the answer, but it will be boring. Let's think together. I will pretend that I'm thinking it, you will be actually thinking. What is convolution of wave functions in terms of vectors and matrices? And so this one is cat, right? When it is vector column, it is a cat. What will be the function when it is with star?
Bra.
Okay, so this one will be bra, which means C1 star, C2 star, C3 star, and then C sub n star. And how do we, by the way, this convolution in direct notation it will be just bra times cat. So how would we express this normalization operation in terms of vectors? If our bra is row vector and cat is column vector.
Is it just a 1-by-1 matrix?
Do not rush. The answer will be one by one matrix because it's y. So we have bra and we have cat. So our bra is the row vector and our cat is column vector. So we need to practice this product. So this will be C1 star, C2 star, Cn star. And this will be C1, C2, C3, Cn. So what will be the result of such multiplication of two vectors, row by column? I am tempted. Can you come and help?
Me?
Yeah. Please. You just sit so close to here, and it is really simple. Thank you, Kenneth, for being brave. So we are multiplying row by column. You just write by finger. So continue this one. C1 star times C1. Then next term plus C2 star times C2. Then just many periods because it is, and then at the end
Sorry, that's times.
times this. Escape.
Yeah, but I'm trying to solve.
Equals, if it is normalized, equals to what?
1.
Yes.
5.
Yeah, thank you much.
5.
5.
Huh?
5.
Equals to 5?
What?
So, that's one.
Sorry, that's me.
Everyone convinced? So the what do you call it? Condition, expression, equation for normalization in discrete basis is product of row by column vectors representing our wave function, right? Agree? So, and typically, if you multiply conjugated but by non-conjugated, it is the same as C1 absolute value square plus C2 absolute value square plus so forth equals 1. Okay? So, how do we apply this fundamental protocol to our example of eigenstate of annihilation operator? I'm going to scroll one slide back. So here we do have coefficient C sub n, right? And we need to make sure that the state is normalized, which means that we need to write down all coefficients starting from 1 to infinity, take square of each coefficient, add them together, and let that it will be equal 1. Make sense? Why? What are you getting back if you do so?
Normalization accounts, no?
But what are you going to find practically? What is the idea? So each of the terms does explicitly include C naught, right? And we write this row, this adding together this normalization prescription equals 1. We can put C naught out of brackets and solve for C naught. So based from the requirement of normalization, we can find C naught. And then the only unknown variable will be mu. Make sense? I already wrote it before. I need to write it over, otherwise it will be boring. I hated so much when I was in undergraduate when someone was showing slides, because there is no time to focus and there is no time to take records, so it was waste of time. I don't know what is your opinion. So C naught is not changed. We just have C naught absolute value square plus C1 is C naught mu absolute value square plus mu square root of 2 times C naught absolute value square plus mu to the power n square root n factorial C naught absolute value square equals 1, right? So we need to solve for C naught. Each of the terms includes C naught absolute value square, which we can put out of brackets. And inside the brackets, we will have 1 plus mu square plus mu to the power 4 divided by 2 factorial. Then I can guess the next one will be mu to the power 6 divided by 3 factorial. And the many terms, mu to the power 2n divided by n factorial. Close the bracket. And it must be equal 1. Should we get scared of this expression, or should we get really happy?
It's not a Taylor series.
Ah, I'm lucky to be with your class. So it's Taylor series of what? If mu squared equals x, it will be 1 plus x plus x squared plus x third plus x to the power n. One plus x plus x squared over square root of no, square root 2 factorial. There are not many simple functions that we are well aware of Taylor series. Just let's list simple. It's one of the famous simple functions.
Exponential.
Yes. See how nice it works. I don't know if it was intellectual breakthrough or you just tried something first, but I will fast one. So whatever was in the brackets will be e to the power mu squared. Right? Catch me if you can in errors, but I think not this time. So it will be c here c naught square times e to the power mu squared equals 1, which means that c naught equals e to the power minus mu squared square root. Right? Solving for c naught. And if you want to look smart, I don't know but if you want more compact, square root of e to the power something is the same as dividing the power by 2, right? C naught equals e to the power minus mu squared over 2. We do, you know. Now, my time is over, and I'm already borrowing a couple of minutes. So if you look how the height of this, so this C coefficient is proportion how much an eigenstate enters into annihilation state, eigenstate of annihilation operator. And the coefficients will form a progression with a nice function. There will be a little less of lower state, a little more with excited, and then it will decrease to 0. Good. Let's hope that there will be a favorite. Yes. Have a nice weekend. You are accumulating through the semester sufficient minutes that maybe I can return you when it accumulates to the whole lecture. Maybe one day you'll come here and
Yes, bathroom.
Okay, we can. Yeah, you got
Get some beer.
You going home? I'm
What?
going home.
oh, okay.
You're able to.
Huh?
Really?
Yeah, good. Thank you.
See, it's this.
Yeah.
Started in Mr. Business.
One weekend.
Have a good day.
Good.